Hello, student. Welcome to this chapter of analog to digital converter. So, in this class, I am going to explain how an analog signal is converted into a digital signal by an electronic circuit. So, the circuit type used here is a counter type circuit. Of course, there are many are there. And first I am going to explain this one, and later I will explain all other methods. So a counter-based analog to digital converter is a high resolution analog to digital converter. A high resolution means the capacity to convert even a very small signal voltage is called as the high resolution. And anyway, I'm going to explain it in detail later. So this counter-based analog to digital converter is a high-resolution analog to digital converter, uses only one comparator and could be constructed with the help of a variable reference voltage source. All these things you will understand when I explain the circuit. So to construct this type of converter, a simple binary counter is taken. So one binary counter is needed here to count the incoming pulses. And the digital output signals will be taken from this counter. And thus, it should be an n-bit counter where n is the desired number of bits. So here we are going to call this as a n-bit counter because it should be able to count the inputs from more than 1 bit. So that's why this n is defined depending on the application. Means what kind of this converter you need, whether you want a 3-bit converter, 4-bit converter. Accordingly, you will have to choose the counter. So that's why where n is the desired number of bits, the output of this counter is connected to a standard binary ladder to form a simple digital to analog converter. So here one concept comes, why this digital to analog converter comes here. One very important point is that all the analog to digital converters have digital to analog converter as a part of it, because digital to analog conversion is the basic need of this process. That's why all converters have this standard binary ladder type circuit which converts the digital to analog. So that will be a part of this analog to digital conversion. And if a clock is now applied to the input of the counter, the output of the binary ladder is a familiar staircase waveform. This is exactly the needed reference voltage for the comparator. So the block diagram of this counter type of DAC is shown here. Not DAC, ADC is shown here. So this is the block diagram. So in this block diagram, this clock will be there. Clock means any a circuit which produces some square waves, so which are coming out continuously. So some fixed frequency clock will be, it can be some fixed frequency clock, so that comes out continuously. And this is the gate and control circuit, which is required to make start and stop of the process here. So this process is started or stopped by this circuit. That's what is called as a gate and a control circuit. And this part is a block diagram. It's a block diagram of digital to analog converter. So actually this part is very, very important. Binary ladder type is there. So this is the digital to analog converter. A part of this analog to digital conversion. So here a counter is there. It is a binary counter. Its basic function is to count the incoming pulses, and level amplifiers are there. The level amplifiers are used to correct the voltage if some small difference is created during this process of conversion. That will be corrected by this amplifier. They are called as the level amplifiers. And this is the binary ladder circuit. It's a resistive ladder circuit that converts the digital to analog voltage. And the output of this binary ladder digital to analog converter is an famous or familiar staircase voltage. Because it is called as a staircase voltage as it increases step by step like this. That's what is called as a staircase voltage. And this staircase voltage from the binary ladder is taken here as the reference voltage, and that is fed to the one of the input of comparator, actually to the negative terminal of the negative input of the comparator. So, and to the positive input of the comparator, the input analog signal is applied, which is to be converted into digital. So this is a comparator circuit, op-amp based comparator circuit. The basic function of this comparator, op-amp based comparator, is to produce a difference voltage. It produces a difference voltage. Many times it is called as the error signal, because two signals are applied here. One is the reference voltage, another one is the input analog voltage. Both are the analog inputs here. So this comparator actually produces the different signal at its output. When these two inputs are exactly equal, that means when the analog input voltage is exactly equal to the reference voltage, the difference of these two signals is 0, then no output is produced by this comparator. That means the output of the comparator is a 0. This is how it works. Then I will tell you how this works. This circuit works. And clock is here. It will be coming inside. And the magnitude of this input voltage is very, very important. So this reference voltage is fed back to the comparator. That's why it is called as the sometimes this reference voltage in this circuit is called as the feedback voltage, because this feedback voltage is drawn from this binary ladder, which is in the output stage. That is why this reference voltage is a feedback voltage. So what happens according to the magnitude of this input voltage? This reference voltage appears here step by step, not directly, not directly. Hmm? So that is why what happens, you see, let us say you have applied some 1 volt here, 1 volt of analog signal. And initially, when you switch on the circuit, the reference voltage will be 0. The reference voltage will be 0. That is why this is 0, this is 1 volt is here, and 1 volt is produced here. Comparator produces 1 volt. So there is an output from this comparator, and that is given to this logical circuit. And whenever there is a input from this comparator, this gate control works. That means gate is open. The control circuit sends the input voltage coming from the comparator and opens the gate. Once the gate is open, the clock pulse coming from the clock moves in this direction, So one pulse appears here. One pulse appears here, and thus that pulse is counted by the counter, and it comes down, its voltage is checked and it is leveled, and that same voltage comes to the binary ladder, and the output will not appear here. The digital output will not appear here until this reference voltage becomes equal to the analog input voltage. So as I told, this is the 1 volt, and just as you switch on the circuit, 1 volt is here, 0 volt is here. So output is produced, and it comes like this. And in the next few seconds, what happens? The 1 volt which is produced here, it comes in this direction, and it comes to the binary ladder also. So feedback of 1 volt is coming out from the binary ladder circuit, and that is fed to the comparator circuits. Now in the next fraction of second, what happens? We have supplied 1 volt here as an input signal, analog input signal, and 1 volt is also produced by the ladder circuit here, and both the inputs to the comparator are 1 volt, and that results to the 0 of the output voltage of this comparator. Now the difference signal is 0 because both the inputs are equal. Both the inputs are having the equal voltage, so the difference signal is 0. That means there is no output across the comparator. And now what happens? This control signal senses that no voltage is coming from the comparator. The control circuit senses that no voltage is coming from the comparator, and immediately it closes the gate. Once the gate is closed, no clock or no pulses produced from this clock cannot move and cannot reach the counter. So that means I can say that the counting process is over, or the conversion process is over. So that 1 voltage which is converted here in this region as a digital voltage. So actually this counter has the facility to store the that pulse also. So that stored information will appear here. As this conversion process stops, that stored information in the counter will appear here as a digital output. That means a digital output of 1 volt appear here in this way. And suppose you think that I have applied 3 volt, then what happens? So initially as I told, here 3 volt is there and here 0 volt is there. Circuit is switched on, and this control and the comparator produces 3 volt, and control circuit is on, gate is open, and the clock starts moving in this direction. So one pulse appears here, that pulse comes down, and that pulse also comes here as the output of ladder in the form of analog signal, and one step is produced here. For that one pulse, one step is produced. So now it is 3 volt and the 1 volt is here, and this comparator again produces the output. So control circuit opens the gate, and one more pulses comes out of the gate and reaches the counter and comes down, and a reference voltage of 2 volts appears here. That means 2 staircases are appeared, and now still the difference voltage is not 0 because this is 3 volt, this is 2 volt, this is 2 volt, and the comparator produces the output that is sensed by this control circuit, and gate is open. Again one more pulses comes, so counter counts it is corrected and comes like this, and one more staircase is produced. That means totally 3 staircases are produced here, and I have shown here just this is for an example, just to show that it is in a staircase voltage. And now we have the 3 volt input and 3 staircases are produced, and now both the inputs are equal, and the output of the comparator is 0, and that is sensed by the control circuit. The gate closes, the counter stops counting, but it stores the 3 voltage in it. So that stored 3 volt in the form of digital comes out down as a digital output. So this is how the conversion takes place, and then this is how the circuit also works. Yeah, so same thing I explained here. Whatever is there, whatever it is written, I have explained. And this is also I explained all these things. It is what happens, I explained. And these all you can read out, just same things is there. And now I will come to this point. What are the advantages of this counter type analog to digital converter? One of the advantages is that it's a very good method for converting an analog signal to digital to a high resolution. So I should talk once about this higher resolution. I will come to that point later. As I told, high resolution means the capacity of a circuit to sense even smaller voltage. For example, suppose if you applied 0.5 volt to the circuit, but if that 0.5 circuit is not sensed by the circuit, because based on the design, certain minimum voltage has to be applied for the circuit. And suppose your threshold input voltage is 0.5 volt, and you have applied 0.1 volt. 0.1 volt is less than the minimum voltage. That is why that will be not sensed. So that means you can't use this circuit for the lower voltages like 0.1, 0.2 like that. So this is what the resolution. So it has a good resolution. You can, according to design, you can even apply the millivolts to get the output. It's simpler than the simultaneous method. Simultaneous method is another circuit that converts the analog to digital, and we can see it later. So it's very simple circuit is that. What is drawbacks? Conversion time is too high, that is in millisecond. This is one of the important factor for the converter circuits. Lower the time, better is the circuit. So that is the point. But in this case, conversion time is too high in millisecond because it counts every pulses. Since the number of bits can be more, the time also increases. To improve the conversion time, one has to use the clock of higher frequency. That is greater than 1 megahertz, one can be used because this is the important relation for this counter type. The maximum conversion time T max is given by this equation. T max is equal to 2 raised to n minus 1 into T clock. So where this n is the number of bits, thus as the number of bits increases, the conversion time also increases. So this is a drawback. But for to increase the sensitivity means resolution, more number of bits are required. But if you raise the bits, conversion time increases. So these are the problems or the challenges associated with these type of circuits. So one has to adjust all these things. Other way to reduce the conversion time is to use of clock of high frequency greater than 1 megahertz. So here T clock is multiplied here. So instead of raising this to n, you can increase this so that conversion time is reduced. So that is a one method. But this works up to certain high frequency only. Beyond that, it won't work as the component subcircuit may not support. So the one idea is to reduce the clocks to use of clock of high frequency. Generally, it is 1 megahertz. You can use more than 1 megahertz clock. But what happens? Even how much you can increase? Can you take gigahertz? No. Again, there is certain limitation is there because the circuit should support that clock what you are using. So this is one of the important thing or parameter regarding the conversion time of this counter type ADC. So this is the details of analog to digital converter, the counter type analog digital counter. So you can go through once or twice so that you can understand. Thanks for listening.